Hello, my name is Teresa Stack. I'm an associate professor at Montana Tech in the Safety, Health, and Industrial Hygiene Department. And this learning unit is part of Principles of Epidemiology, the master's class. And it covers different measures of disease frequency and distribution in our population. As a review, there are two broad categories of epidemiology and the way in which we study disease and describe disease that is within and upon our population. So the first one is descriptive studies or observational studies. And this is concerned with the distribution of disease as categorized by time, place, and person, and also the rate at which disease is occurring in our population. So we use these different measures of disease frequency or disease occurrence to describe our observational studies. After gathering data from our observational studies, our cohort studies, our case control studies, we generate a hypothesis, and that is a different category of research called empirical or analytical epidemiology. And that's where we generate a hypothesis and we used a randomized control trial to study the different occurring rates of disease, the different risk factors of disease, and that is distinctly different than descriptive or observational studies, although one does lead to the other. What are some outcomes that we measure in epidemiology? Death, disease and illness, such as physical signs or laboratory abnormalities in a sample, risk factors such as smoking height or occupational exposures, discomfort and symptoms, disability and prevention. The first three we probably spend the most time talking about in this class because it is the easiest way to describe disease in a population to a wide range of individuals with different backgrounds. So we're not making you all epidemiologists, but we're trying to expose you to what the different measures, rates, and terms mean so that you can better interpret scientific research when you're drawing your own conclusions. The measures of disease frequency can be used to quantify the burden of disease on a population. For example, how many people have a certain disease or how many people are getting a benefit from taking a certain vitamin or intervention. It provides us a basis for a fair comparison amongst and within populations, for example, globally, the US versus the UK. It also provides an estimate of risk for individuals within a population, so related to a certain time, place, or person. So for example, the risk of cancer is 5 times higher in Butte, Montana than it is in Houston, Texas. And that certainly isn't a valid statement, but that's an example of ways in which we can use epidemiological data and these measures of disease frequency. And as you can see, I highlighted the word population because population is really important. The different statistical methods, the different data sources that we use and ways that which we express epidemiological data are ratios, proportions, rates, and then of course risk. And in all of these you can see that in our mathematical equation, B is the population. And so who this population is, where we got them from, and how we're trying to use this population to generalize to a larger population is all really important in the interpretation and the understanding of our epidemiology data, and really all data related to health and interventions and maybe even medical studies. And we're going to talk about the sources of databases later on in the course, but I wanted to just introduce the idea of a population and different types of populations and terms that are used in the study of epidemiology. And the first term is your target population. And your target population is simply the population which you hope to make an inference about. So you're going to choose a small sampling of individuals or maybe study a cohort of individuals and then make a generalizable statement about a larger proportion of individuals. And that larger proportion would be considered your target population. The next type of population is your study population, and your study population should not be confused with your sample population. So your study population is very similar to your population at risk, and your study population is those individuals which could possibly be study subjects. So all these people meet certain characteristics or have certain determinants, and if chosen by random, they could have been part of my sample population. And the difference between your study population and your sample population is your sample population are those people you actually pick. So think of it this way. In your workplace, let's say you have a large group of individuals who perform welding. 90% of their job is welding. Your study population would be all those individuals who weld. But you conduct your air monitoring sampling or your noise sampling on a smaller subset, and that would be your sample population. Now, if you sampled repeatedly, you might draw some conclusions and make inferences about your target population. And your target population could be those individuals inside of your corporate company, so all your different sub companies together that perform the same type of job. So similar exposure groups across different divisions inside of one company could be your target population. And how your target population differs from your study population and how it differs from your sample population is very important when you interpret your results as an industrial hygienist or as an public health specialist, as well as the way you use data and be able to interpret data that you may be reading to draw some conclusions about the occurrence of disease or which control measures work best inside of for a certain disease that you're studying. There are five main types of measurements used in epidemiology. And the first one is the count. And the count is simply the number of disease events or incident cases. And it's a pretty simple measure of disease frequency during a certain time period. And it could tell us something about healthcare resources needed. So, for example, we may need to know that it's going to be a low number of flu cases this year, and therefore we won't need as many public health nurses or as many immunizations as if it was going to be a high number of flu cases in a year's period. So counts are used, but they're not very descriptive. And then the second form is a ratio. And don't think of a ratio as a proportion as you see below, but think of a ratio as, for example, we have 30 students in this class, and if 10 are male and 15 are female, the ratio of male to female would be 10 to 15, and of course that would make a total of 25 students in the class. So in a true ratio used in epidemiology, A plus B equals the total population, unlike a more common measure, which is a proportion, and that's where the total number of people is in your denominator, and some proportion of them is in the numerator. So what's the proportion of people in our online class that currently have a headache? Well, we have 30 students, and if 3 of you had a headache, that would be 30% of you. The next one is the rate, and when we look at a rate, it's similar to miles per hour, and it's the quickness in which the disease is occurring in our population, the rate at which it's occurring as opposed to the proportion of it inside of our population. And then we use risks to, we use actually a ratio. We actually use rates placed one over the other to estimate risk, and that would be the probability of developing disease over time. There are two main types of categories that we use when we describe disease in a population. One is prevalence, which is the existence of disease. So what's the prevalence of HIV in Butte, Montana versus the incidence? And the incidence is the number of new cases of HIV in a population. So right now we're going to talk about incidence. The difference again between incidence and prevalence is incidence is the frequency of new disease occurrences over a specific period of time. And it's applicable to any disease. If the disease itself is an event or acute in nature, it refers to the frequency of that disease event over time. If the disease is a chronic state or chronic in nature, it refers to the frequency of the onset of that disease, so when that disease begins within a certain time period. So we can talk about incident disease events. And an event would be the same person may have multiple experiences versus an incident disease case. And in a case, each person is counted once. So I'm not going to distinguish between events and cases in this class, but to realize that they could change the way in which cumulative incidence as well as incidence density and incidence rates are calculated. So now we'll work on an incidence problem. This will help you more understand the definition of incidence as well as allow you to do some calculations. So here we just have a basic plot. On one side, on our y-axis, we have the number of people at risk. So in our study, we had 10 people. And on the x-axis, we have our time observed. So we observed these people for 5 minutes. And so let's say we had 10 people in a room and we were filling it up with carbon monoxide, and we wanted to see how long it took for somebody to experience a headache. So the outcome is a headache. We have 10 people and we're going to observe them for 5 minutes. And so each one of these stars represents when the person had their headache, or more generally speaking, when was that onset of the disease. So we have 2 people who had a headache in 1 minute, we had 1 person who had a headache in 3 minutes, we had 1 person who had a headache in 5 minutes, and the rest of the people didn't have a headache at all. So they were totally fine. And so now let's calculate our incidence rate. So our incidence rate is simply a count of the number of incidents. So we had, or the number of events, I'm sorry. We had 1, 2, 3, 4 over the population, which was 10. And if we multiply that by 100, we have a 40% estimated risk of developing a headache in our 5-minute period. So with cumulative incidence, the time period is the total observation period. So everybody is assumed that they are observed for the total time period, the entire 5 minutes. And we had 10 people that were observed during this time. So our estimation of risk is 40%. You have a 40% probability of developing a headache when you're exposed to carbon monoxide in a 5-minute period. And that's our basic calculation for cumulative incidence. And here is a chart I'm going to have you take a look at. So this is the incidence rate of pertussis by age group. So it's a count, and you can see that incidence rate here is per 100,000 people. And it looks like you're more likely to develop pertussis if you're 1 years old than if you're 20 years old. So cumulative incidence is a proportion. There are no units. The numerator is in the denominator. So that means that the number of people that have the disease is also part of your entire population. It's for a specific time period. This was for a 5-minute time period. It provides an estimation of risk. If a person was chosen randomly from the population, they had a 40% risk of developing a headache. It assumes, again, the entire population is observed for the entire time. And some other words that are used to describe cumulative incidence are estimated risk, attack rate, cumulative incidence, or incidence proportion. The problem with cumulative incidence is we often do not observe all members of a specific population for the entire time period. So here we were only talking about an exposure of 5 minutes, but what if we were studying people for 10 years? People may leave the study because of other factors that affected their health. You may lose them because of follow-up. They may pass on and not be part of your study. Sometimes you have people that enter and leave the study. So that is one issue with using cumulative incidence. So it doesn't take into account a dynamic population. Also, it doesn't really represent well how fast a disease is moving inside of a population. It only gave us a proportion. In a 5-minute period, out of 10 people, 4 of them, or 40%, you had a 40% probability of developing a headache if you were exposed to carbon monoxide for 5 minutes. So another way to think about this is how many minutes were each person in our study. So if we had 10 people who were in our study for 5 minutes, we had 50 person minutes. And this may give us a better indication of the rate at which the incidence is occurring. And it also allows us to not count the minutes of people who've already had the onset of that disease, because the probability of having the disease once you've already had it would be 0 because you've already had it. We shouldn't be counting you anymore in our denominator. And so to do that, we call this rate either an incident rate, or this term is also called incidence density. So here again, we have our population. So another way of thinking about this is, are we measuring one person for 5 minutes? That would give us 5 person minutes of time. Or are we measuring 5 people for 1 minute? This would also give us 5 person minutes of time. Which one is more accurate? And so what we're trying to do is come up with the number of people per time of their observation, which gives us a closer look at what's going on with our disease. So our incidence rate, or our density, is the number of new cases of a disease in a specific population during a time period over the total person time at risk. So person time is the number of people times the time of their exposure. So we need to change our chart just a little bit. So you're looking at what our new chart would look like if we were going to calculate cumulative incidence. So what this represents is everybody started the study at the same time. Person number 1, or person number 10, I'm sorry, completed the entire study, 5 minutes, and never had a headache. Person number 9 completed the study for 4 minutes but dropped out for some reason other than a headache. Person number 8 had a headache right there in the first minute. Person number 7 went for 3 minutes. Person number 6 had a headache in the first minute. and so on. So you can see that we still had our 4 events, but instead of using as your denominator the total number of people in the study, you use the total time each person contributed to the study. So person number 1 contributes 3 minutes. And person number 2 contributes 2 minutes. And person number 4 contributed 3 minutes and then developed a headache. And person number 5 contributed 5 minutes. And so when we add up all of our numbers, 1, 4, 1, 3, 3, we come up with 29. So our group of 10 people cumulatively contributed 29 minutes to our study. So we take our 29 and we multiply it by the number of people that were in our study, which was 10, and that means we had 290 minutes of person time observations, and we still had our 4 cases. So let's take a look at what that data would look like. So person time at risk is the specific amount of time over which a person is observed. And so we stop observing the people when they are no longer at risk. This is different than taking our average, as we did when we were looking at our proportion, which we assumed that everybody was observed for the full 5 minutes, when in reality everybody was not observed for the full 5 minutes. So when we do our calculation, we have 4 events again, 10 people times 29 minutes, and which would be 10 times 29 is 290. So we take our 4 and we divide it by 290, and we get 0.013 cases per person minute. If we multiply that by 100, we would get 1.3 cases of headaches for every 100 person minutes observed. So now we know the rate at which the headaches are entering our population. That would be 1.3 headaches for every 100 person minutes, new cases that are observed. And this gives us our rate. Our incidence density is a rate. It has no units. It is not a proportion. Our proportion is our incidence density. So it gives us an idea of how fast this is occurring in our population instead of the proportion of the population that is likely to develop the disease. So some other aliases for incidence density are our hazard rates or force of mortality. A person who becomes sick as a case contributes person time to our data set only until the point in time in which they become sick. So now we can look at some incidence rates per 100 full-time workers across the United States. So if you get hung up on this person time, incidence rates when we do our workplace calculations are really looking at person time hours as well, and we're normalizing it to 100 full-time FTEs, and that's when we use that 2,000 hours worked a year times how many workers that we have. We're normalizing our data, and that is hopefully an analogy that will allow you to understand how that's similar to using incidence density and gives us a true rate instead of cumulative incidence, which is our proportion. So now let's just take a look at the way disease can travel through a population. This explains how human movement in a heterogeneous propagation of dengue fever in Cambodia. And you can see how the incident rates, the cases per 100,000 people per week change and plot themselves across time. So some other types of incidence rates. Crude rates are summary rates based on the actual number of an event, such as a birth or a death, in the total population over a given time. Um, a strata-specific rate will allow us to compare characterizations. So we calculate only for a specific population. Usually it's broken out by age, sex, race, or ethnicity. And so our example here, you can see that this is suicide mortality rates by age and sex in Utah. And we can do a comparison by age, and we can also do a comparison by gender. And it really is quite disturbing, the suicide rate by gender, if you look at the 65 and plus category, and that male rates are significantly higher than our female rates. So we can also, if there are differences in population, then we would use an adjusted rate. And we'll talk a little bit more about adjusted rates later. So rates whose denominators are the total population include crude birth rate, crude death rate, age-specific death rate, and cause-specific death rate. So death rate, for example, from cancer. Death rates whose denominator are live births include infant mortality rate and neonatal mortality rate. Infant is under 1 and neonatal is under 28 days. So adjusted rates allow us to do a fair comparison, and we actually recalculate the rate according to a certain distribution. So for example, if you have a higher percentage of males in our population in 2001 than you did in 2015, then we really can't make a fair comparison of a rate between 2001 and 2015. Instead, we would take one of those years and age adjust it to a common census. So here you can see that the age-adjusted rate for unintentional injuries was adjusted to the 2002 population. So we take our 2006 rate and we adjust it to our 2001 population rate, and now we're able to make a fair comparison. And we will talk more about adjusting rates later. So here is our in-class exercise. Go ahead and take a moment and see if you can calculate your female death rate, cancer rate, and overall death rate given the population that you have.